Hello, AP Chemistry kids. I know today's a snow day, but the AP test is on May 5th, and they're not going to change the date. So I thank you for your time for watching this lecture. It's going to cover the rest of Chapter 5. I'm not going to go over this in class, so this is the way you're going to get it. The rest of the chapter is, we're only going to look at the conceptual concepts. In other words, all of the things that I'm going to show you today are not calculated problems on the AP test. But all of the pieces of information that I go over today can be found in conceptual questions. Alright, now I see when I've imported my PowerPoint that some of the symbols did not import. So this box right here is supposed to be an equal sign. So that should be equals, and at the bottom this is supposed to be the proportional sign. So it shouldn't look like that. It should look like... Oh, that wasn't good. Let me erase that. It should look like the proportional sign. I didn't even draw that. It looks like a crab. Anyways, average kinetic energy is proportional to the Kelvin temperature of a gas. Or you can just put in an equal sign in there too, so don't look at my bad drawing. Okay, so this is the kinetic molecular theory. It helps us build a model for how ideal gases behave. Okay, remember I said ideal gases. At the end of this PowerPoint, we're going to talk about that gases at certain conditions don't behave like ideal gases. Alright, so we're going to talk about the ideal gas laws, and this molecular theory helped develop the ideal gas law. And it has stated that the individual particles, the volume of the particles is zero. Now we know that's not true because if it exists, it takes up space. But we're going to pretend like they don't. And the collisions of particles cause pressure. We've already talked about that. And that particles don't exert forces on each other. So they're saying that all those forces of attraction do not occur, but we also know that's not true either. And the last thing that they're going to assume is that average kinetic energy is equal to the Kelvin temperature of a gas. And we have already kind of mentioned that kinetic energy equals that temperature. Okay, so we have two ways to look at temperature. We can look at it per mole, and we'll use the very first equation for that one, per mole. And, oh, I have a fancy pen. Look, oh, this equation we could use per mole, but this equation, whoa, the whole page moved. I guess I have to press that. Ooh, this equation represents per molecule. The one that's at the bottom is more commonly used. You will have to probably come back to that. And again, the symbol here, right here, should be an equal sign. So kinetic energy equals 1/2 mv squared. Now, we have to look at this top equation and decide which R should you use. So when we're speaking here, which R should we use? Well, remember, kinetic energy is in joules. So we're going to have to use the R that has joules in the units. So the R has to be what I'm going to start calling the energy R. So whenever you hear me say energy R, oh, energy is in joules. I need the one that has joules in it. So when you look on your orange paper, you're going to use this one, okay, because it has joules per mole Kelvin. Now both of these equations seem to make sense if you think about that. Kinetic energy is energy of motion. If you increase the temperature, so if the temperature goes up, the kinetic energy is going to go up. And so we use this relationship to explain the motion of molecules, and thus we say that is equal to the Kelvin temperature. Going back to the equation that kinetic energy equals 1/2 mv squared, let's take a look at the v there. Okay, that v is velocity, and what we're going to do is take the average velocity. So if we look at the average velocity, the way they're going to figure it out, it's the average of the squares of the particle velocities. And so this is just a special way of trying to get an average velocity. They take the square root of the velocity and they call it root mean square. So this is a common term. Okay, root mean square velocity, or remember that velocity is also a measure of speed. So we're going to figure out how fast these molecules are going. So we're going to use this equation at the bottom, and again, the symbol didn't come through in the PowerPoint, so this is supposed to be an equal sign. So the root mean square velocity is equal to the square root of 3RT over the molar mass. Now we have to be careful here that molar mass has to be in kilograms, and the R has to be the energy R, okay, energy R, because we need to have joules in the end. And then I know you're saying, well, velocity is not going to have joules, but the way that we get there is that a joule is equal to a kilogram times a meter squared over second squared. And so you can see that kilograms are going to disappear from the molar mass, and you will end up getting meters per second once you take the square root of this second part of the joule unit. Alright, let's do an example problem looking at root mean square velocity. So we're going to calculate the root mean square of CO2, so this one is CO2, versus helium. And we're going to have them at the same temperature. Alright, so the root mean square is 3 times the R value times the temperature, 303, and we divide it by the molar mass. Remember, the molar mass has to be in kilograms, so this is kilograms. And so we did CO2, we got 414 meters per second. So that's how fast the CO2 molecule is moving at 303 kelvins. Then let's do helium. Same calculation, but the molar mass is different, so our molar mass is down here for helium, and we get 1.37 times 10 to the third meters per second. Whoa, helium is way faster than carbon dioxide. Well, it seems to make sense, because if you think about it, a lighter person can move a whole lot faster than a heavier person. I said can, not for everybody. So that's exactly what's going on here. The lighter molecules, lighter atoms, move faster than heavier atoms. That's an important fact. I think it's interesting to look at where the formula for diffusion and diffusion came from. It comes from their kinetic energy at any given temperature. So all you're doing is comparing the kinetic energy of one to the kinetic energy of another. That's right here. And so we can substitute the kinetic energy with 1/2 mv squared formulas. And then let's rearrange them. We have a half on each side, so the first thing I did was I crossed off the half on each side. And then I divided by m1 to isolate the v1 on this side, so that's where we're at right here. And then I moved the v2 to the left-hand side. And since these are squared terms here, I took the square root of both sides. So now we're at the velocity of 1 over the velocity of 2 is equal to the square root of their masses. And so that's exactly where we get the diffusion and effusion from. And I want you to notice something here. This is really important. That at the top we have V1 right here, V1, but at the bottom we have the mass from the first one. So they're opposites. That's an important factor when you're going to use the diffusion and effusion formula. These formulas are on the AP test, so you will have to calculate with these. So here we have the formulas, so they look a lot nicer. Again, we had a problem with the PowerPoint. This should be an equal sign. This should be an equal sign. And so we can use the rate of effusion or diffusion. Same with the distance traveled, they're proportional. But just remember that if you have a 1 here, you have a 1 on the bottom. Okay, if you have a 2 on the bottom, then in the molar mass, the 2 goes on the top. Okay, so M stands for molar mass. Alright, let's take a look at a problem. Alright, I'm going to do the sample 5.20, which is on page 220. It says calculate the rate of effusion of hydrogen gas and uranium hexafluoride. Alright, so we're going to put the rate for H2 on the top, and we're going to put the rate for uranium hexafluoride on the bottom. Now remember, when we do the masses, we have to put them opposite. So I'm actually going to do this on purpose. I'm going to put hydrogen on the bottom first, and then we'll put uranium hexafluoride on the top, and go ahead and figure it out, and we're going to find out that hydrogen diffuses 13.2 times faster than uranium hexafluoride. Now it makes sense. The lighter mass moves faster. The heavier mass moves slower. That's an important concept. Alright, the last thing that we're going to speak about is a real gas versus an ideal gas. So far we've been talking about ideal gases. And ideal gases behave as expected at low pressures or high temperatures. We're good with that. But a real gas does not behave that way. So if we want to speak about a real gas, we have to correct their behavior when we get to the high pressures and the low temperatures. Why at high pressures? Because at a high pressure you have a smaller volume, and that means that the volume of the actual gases matters. And at low temperatures, the molecules aren't moving as quickly, and the attractive forces become important here. Alright, this is the correction factor, or the equation that you would have to use when you were speaking of real gases. And real gases behave differently than ideal gases at high pressure and low temperatures. And so we have this equation. This equation has a name. It's called the van der Waals equation. This V should be lowercase, by the way. And so what it does is it takes the ideal gas law of P V equals nRT, and it puts in a correction factor. So we can't use the obvious value for P. We have to make it corrected for at high pressures, and we have to correct the volume under those conditions of high pressure and low temperatures. And so once you put those all in there, you would get some values that are closer to what the real gases display. Now, you won't have to use this equation again on the AP test, but you may have to explain that real gases behave differently, and you must have to explain the conditions at which they behave differently. Alright, this is the end of what I wanted to do in class today on the snow day. And so if you would read section 5.8 carefully and understand the graphs, also look on your note sheet from that Miss McCormick note sheet that I use in class, and look at what she's speaking about those graphs. And then finish the gas law problems on page 86, 87 of the lab manual. I already put the answers on Edmodo. Yesterday you were supposed to do half of them, and then today I would like you to do the rest of them. Again, if you have problems, put a mark by them and we'll discuss them in class. But I need to see a good effort. Alright, enjoy your day. Thanks for working on your day off.